Hi everybody, my name is Dave Morgan. Hopefully you found this video because you saw my poster presentation at the American Association of Physics Teachers Conference. I promised a link on that poster to a discussion of the topic in a little bit more detail. Here's the poster here. If you didn't see that poster, I'll spend a little bit of time talking about that, and then we'll talk about some of the points that I sort of didn't have room to make in the poster. So the poster was based on this puzzle that I encountered online about a year ago, I would say. And the puzzle was amusing to me because the amount of fighting it caused in the Facebook comments. And I spent a lot of time trying to convince people online that, their fighting was in vain, because the problem with the puzzle is it does not have just a single right answer. So here's the puzzle. At the top you have a bunch of polygons that add up to 45. In the second row you have some bananas plus some polygons that equals 23. Row 3 you've got bananas plus 2 clocks equals 10, and the bottom row is clock plus bananas times a bunch of polygons equals what? And you're supposed to find the answer to this puzzle. One of the things I said in my posters, we're not interested in the fact that this last operation includes a combination of multiplication and addition with no parentheses, so there can be some arguing about order of operations if people don't understand what order they're supposed to do the addition and multiplication. That's not what I want to talk about. What I want to talk about is the ambiguity of the puzzle itself. So let's take a look at some of the different ways that this puzzle can be interpreted. So here I've got the puzzle written out on the board, and the simplest way to interpret the puzzle is that we've got polygons plus polygons plus polygons equals 45. They're all the same. The only way three identical things can add up to 45 is if they're equal to 15. So a bunch of polygons is equal to 15. If bananas plus polygons equals 23, and the polygons equals 15, then bananas plus bananas equals 23 minus 15, which is 8. And the only way that two identical things can add up to 8 is if they're both worth 4. Then in this row, we've got bananas, which equals 4, plus clock equals 10. That means clock plus clock equals 6. That means clocks are worth 3. So if you take that interpretation to the final row, which says clock plus banana times polygons, what does that equal to? Well, we just said a clock equals 3. Bananas are equal 4. The polygons is equal to 15. So 4 times 15 equals 60. And 3 plus 4 is 7. So the answer, according to that interpretation, is 67. And if you buy that interpretation of the meanings of the symbols, then you understand order of operations. That's the answer you should get. Unfortunately, some people look at the meanings of the symbols and they read a little bit more into those symbols than is maybe justified by the examples given. There's no argument that this plus this plus this equals 45. There's no argument that this plus this equals 23 and this bunch of bananas is 4. And there's no argument that this clock that reads 3 o'clock is equal to 3. But when you come to the final question, they look at this clock and they notice, well, this clock doesn't read 3 o'clock, it reads 2 o'clock. So if the 3 o'clock clock means 3, then the 2 o'clock clock must mean 2. And if you look closely at these bananas, that's not 4 bananas like in the examples, that's only 3 bananas. So maybe the reason these bananas were equal to 4 is because there's 4 bananas. So 3 bananas equals 3. And if you look at these polygons, they're different from these polygons. These polygons in the first 2 examples were a hexagon, a pentagon, and a square. That's 6 sides plus 5 sides plus 4 sides, or 15 sides. So the reason this is equal to 15 is that there's 15 sides in those nested polygons. In this example, it's only a hexagon and a pentagon, which is only 11 sides. So the people who interpret the puzzle this way say that this is not 3, 4, 4, and 15. This is 2, 3, 3, and 11. 3 times 11 is 33. 33 plus 5 is 38. So how you interpret the answer to this puzzle has a lot to do with how much meaning you read into the symbols. And the point that I tried to make when discussing this online with people is that the interpretation of these symbols leaves very much to the imagination, because only one example is given for each of these symbols. When we look at the original puzzle, all we know is bananas plus polygons equals 23. We don't know if it makes any difference how many bananas there are, because we're never given an example with anything other than 4 bananas. We don't know if it makes a difference that the clock reads 3 o'clock or 2 o'clock, because we're never given a worked example to show us whether a clock with a 2 and a clock with a 3 means something different. Likewise with the polygons. We have no reason to believe that the reason these polygons add up to 15 is because they have 15 sides. We're only making that logical jump because we're looking for a meaning or a reason why the symbol means that number and not some other number. And the point I made in the poster presentation is that this is a really good example of the difference between math and science. And it's a really good example of when you're constructing a scientific theory. Scientific theories are always underdetermined by the data. There's always a finite amount of data. And because there's always a finite amount of data, there are always multiple theories that you can generate that explain that data. So in this case, we can generate easily 2 different theories. One, that any bunch of polygons is 15, any bunch of bananas is 4, and any clock is 3. Another, that you count the sides of the polygons, you count the number of bananas, and you count what number the hour hand of the clock is set to. Without any data to discriminate between those choices, without any examples that allow us to tell which of those theories is right, there can be no one right answer. So it's pointless to argue about whether the answer is 38 or whether the answer is 67, because you're simply not given enough information. This is a useful exercise for students in that you can ask them to give an example of what additional information would support one theory or the other. So suppose you're a proponent of the polygons are 15, bananas are 4, and clocks are 3 no matter what. What additional example, what 4th example here could be given that supports that theory? If you're a proponent of the count the sides, count the bananas, and read the clock theory, what additional example, what additional data would you look for that would support your theory over the other theory? In the philosophy of science, this is sometimes called an experimentum crucis, or a crucial experiment. What is the crucial experiment that would discriminate between 2 competing scientific theories? The other thing that I wanted to talk about, and I didn't sort of have room to point out in the poster presentation, is that this puzzle presents itself as a mathematical puzzle and a logic puzzle. And as such, it doesn't really do a very good job as either of those things. And the reason is sort of built into the difference between how mathematics is done and how science is done. In mathematics, you start with certain definitions, certain rules, certain postulates, and you use the rules of deductive logic to generate results, answers, theorems, and proofs. And the way mathematics works is if those definitions and postulates and rules are accepted, then the resulting theorems and answers that you get are logically sound. That's not how science works. Science works through a process of inductive logic. You start with a finite amount of observations, measurements, and data. And you use inductive logic making generalizations, looking for patterns, looking for rules, what we call laws, to explain collectively those observations and that data. And those explanations we come up with are called theories. In this case, we look at the information we're given, these three examples of the meaning of these symbols, and we construct a theory that explains how they work. The problem is there's only a finite number of examples. So we can generate multiple theories that explain what these things mean. The process of induction is always incomplete and it's always imperfect. And we can never be sure that the answer we get from induction is correct. All we can do is come up with more and more and more data, give more and more and more examples, and see if the theory we came up with explains those examples. One example I like to give when I'm talking about this basic idea to students is the example of looking at the world around us and constructing generalizations about that world. If you've lived all your life looking at birds and you see crows, it would be a very, very simple generalization about the world to say all crows are black. Every time you see a crow and it is black, it is an additional data point that confirms your hypothesis that every crow is black. And that's a perfectly reasonable generalization from the available data. The problem is the available data is always finite, and it's always possible in looking at the world that the very next crow you see will be white, thereby destroying your hypothesis or requiring you to change that generalization, to modify your theory to all crows are black except those with albinism or another pigment defect, and those are very rare, but those can be white. It's not as pretty a law, but that's how scientific laws work. They need to become more and more precise over time as our available data becomes greater and greater. There's another example that I sometimes use with students when I'm talking about particle physics and how we know, for example, that there are particles called quarks, and that is my quarks and Easter eggs puzzle. Imagine you had a basket full of plastic Easter eggs, the hollow kind that you can take apart and put candy inside. And you weren't allowed to open them up to see what was inside, but you were allowed to weigh them. And you've got a great big basket full of these eggs, maybe 50, 60, 100 eggs. And when you weigh them, you find that there are only certain weights that appear. You have 1 gram eggs, 4 gram eggs, 7 and 11 gram eggs, 14 gram eggs, and 21 gram eggs. And you never find any other weights. Can you construct an explanation for what the weights are of the candies inside that explains the weights that you see? 1, 4, 7, 11, 14, and 21. Now, one example could just be that there are jelly beans in the eggs, and jelly beans weigh 1 gram, and so this one's got no jelly beans in it. The egg itself weighs 1 gram also. So here's our theory. An empty egg weighs 1 gram, and a jelly bean weighs 1 gram. So the 1 gram's eggs are empty. The 4 gram ones have 3 jelly beans. The 7 gram ones have 6. 14 gram ones have 13, and so on. That's a perfectly good theory for explaining why we see 4, 7, 14, 21, and 11 gram eggs. But it doesn't explain why we don't see 5 gram eggs, 13 gram eggs, or 22 gram eggs. The theory should explain both what we do see and what we don't see, and it should do so in the simplest way possible. So I asked my students to come up with a possible explanation for why we see these weights and no others when we weigh our Easter egg. And you can come up with multiple explanations. There's no one explanation that fits all the data. What we learn from that is the same idea of underdetermination, this idea that a finite number of eggs is never going to give us enough information to distinguish between two competing theories. But we also learn something important about how scientists actually know certain things about the universe. For example, if you look at the Quark model in particle physics, The fact that we believe certain subatomic particles like protons and neutrons are not actually elementary. They're made up of these smaller particles called quarks. And there are up quarks and down quarks and strange quarks and charmed quarks, and they all have silly names. But scientists are pretty sure these things exist, despite the fact that we're not allowed to open up the Easter eggs, in a sense. We're not allowed to peek inside of a proton and see the quarks. We can just sort of weigh these particles and look at their various properties and deduce by looking at patterns the same way we do in the Easter egg puzzle what might be going on inside of there. And the resulting quark model is the same kind of inductive model that comes from looking for an explanation of something invisible that's hidden from our observations, but that we can construct a theory, an explanation for, using the process of scientific inquiry and the method of induction. So I encourage you to explore this puzzle with your students. One of the things that the idea of underdetermination forces you to reckon with is, if you can't tell the difference between two scientific theories, how do you choose which one? Or if the data always isn't enough to allow you to distinguish between two scientific theories, how do you determine which one to use? And in my presentation, I talked about what we sometimes call the internal virtues of a scientific theory. How simple is it? How elegant is it? How easy is it to use? How efficient and effective is it as an explanation? So you can have your students come up with other alternate explanations for this this puzzle, other than bananas are equal to 4 and clocks are equal to 3. You can have them try to come up with the most complicated explanation you could. And you could give them something like this. Based on whatever your explanation is of the meanings of the symbols, what is orange plus orange plus orange? Now, none of the examples have an orange in them. So you have to do a lot of logical leaps to come up with an answer to this. Maybe an orange is worth the same as a banana because they're both fruits. Maybe an orange is worth the same as a clock because they're both round. So you can have the students struggle with, when you've got a scientific theory and you get something unexpected that you've never encountered before, how do you work that new information into your scientific theory? And that is, to a very large extent, what the scientific process is about. So I hope that added a little bit to the presentation. If you want to contact me to get more information about any of these activities, either the Facebook puzzle or the Easter eggs puzzle, I'd be happy to share. My email address is dmorgan@gmail.com. And thanks for watching.